Hi, I'm Old Doc Charles. Welcome to this Basics of Electrical Engineering. This is part 3. I'm going to talk a bit about magnetism. Traditional to include an introduction, so here's an introduction, and this is all the shit I'm going to talk about. As I described previously, electricity and magnetism are basically two sides of the same fundamental force. And like electricity, magnetism has similar properties. For example, the magnetic force is measured in what we call the Tesla, named after Tesla himself. The units are kilograms per ampere second squared. Magnetic flux, which is the magnetic density, is measured in the Weber. The units of that are it's kilogram meter squared per ampere second squared. Magnetic reluctance is kind of like resistance. It's not named after anybody. It's ampere squared, second squared, per kilogram meter squared. Reluctance is really the magnetic equivalent of resistance. Magnetic fields follow the path of least reluctance, just like current will follow the path of least resistance. And here's the thing.
Hello, so, here there are two magnets, and there is a magnetic field between them. The magnetic field exists in the air, which has a high reluctance. There is a piece of metal, iron is best as it has a very low reluctance. When the iron is moved towards the magnetic field, it deviates towards the iron because it has a much lower reluctance than air. The closer it gets, the more the magnetic field deviates more and concentrates in the iron. It's part of what goes on in magnetic attraction. So there.
Magnets have both a south pole and a north pole. Magnets come in many different shapes and sizes. They all have one thing in common, and that's they all have a south pole and a north pole. A force exists between poles. Opposite poles attract. You can see here opposite poles attracting. Like poles repel. So here's some repelling like poles. This is kind of important when we come to talk about how motors work. Objects that contain iron, nickel, or cobalt can be magnetized. Here's the thing.
Here we have an ordinary iron nail. If we look at the nail close up, what we see is that the material that the nail is made from is divided up into these little 3D spaces. Each of these spaces has its own little magnetic field, with a north and a south pole. When a magnet is moved towards the nail, its magnetic field starts to interact with the individual magnetic domains in the nail. And they begin to line up, which attracts it to the magnet. The magnetism builds up until the nail is fully magnetized. And the nail and magnet stick together.
Some materials, we can permanently magnetize them, while other materials can only be magnetized when they're actually in a magnetic field. Here's the thing.
So here we have a nail and a bolt that are currently far away from the magnet. When they are moved together, you can see that the fasteners start being attracted to the North Pole, and when they come into contact with the North Pole, they then become fully magnetized. And then when you move them back apart again, the magnetic effect reduces. The bolt retains some of that magnetism. So when you then move them in again and out again and then again out again, you do that a few times and eventually the iron nail remains unmagnetized, yet the steel bolt become fully magnetized and is therefore a magnet itself.
A magnetic field exists between the poles, and we usually represent these fields by lines of equal magnetic force. They're kind of spread out as they go around. They're mostly concentrated at the poles. We can get a magnetic field by using a permanent magnet, which is a thing that's always magnetized, or we can create a magnetic field due to the motion of an electric charge, a current. Here's the thing.
Now what happens here is when we close the switch, a current flows through the coil and a magnetic field builds up. When we open the switch, the magnet field collapses, and the energy is rapidly dissipated across the opening contacts of the switch.
If we insert a rod of iron into the coil, that actually increases the strength of the magnetic field. And you can see that the coil with the iron inside of it gives you a much bigger magnetic field, and that's important in things like motors and transformers and all sorts of crap like that. Magnetic fields are actually perpendicular to electric fields. In this graph, you can see that we have a positive and negative for the electricity going vertically, and the magnetic field is at 90 degrees to this, so it's on the horizontal axis. The other thing is that current and a magnetic field will create force along what's effectively the t-axis, the time axis, going this way and that way. And you can work it out by using the right-hand rule. Here's the thing.
So here we have a copper wire. And if we pass a current through it, a magnetic field is created, and we can measure the direction of it by using a load of compasses, and what you can see is that the electric field is along the wire and the magnetic field is outwards around the wire, or at 90 degrees. The magnetic field is like a tube around the wire. If we place a magnet in the field, then what will happen is the magnet will begin to rotate. And this is how motors work, one magnetic field trying to catch up with another.
So really, that's all we kind of need to know and understand about magnetism. We don't need to go far too deep in it. Yeah, so here's a recap. This is all the crap I've talked about. I think, that's kind of it really for this short part. Thanks for watching. Now we kind of know what we need to know about magnetism. We don't need to go too deeply into it. Yeah, I'll be back in future parts to talk more about the effects of magnetism, which is really the important thing that we need to kind of understand. I think that need be all.